Now, resource allocation is a key theme that will be recurring throughout the course. In today's lecture, we will see two different philosophies of allocating resources. Now, the resource could be time, it could be frequency bands. In orthogonal resource allocation, it says that I'm going to chop up one of these axes, say time, and then give different users different slots. For example, Alice talk, now Bob talk, now Alice talk, now Bob talk. So no two people will actually talk at the same time. Now, clearly this is hard to implement in a large cocktail, but in certain technological networks that is feasible. Or I can chop up the frequency dimension into different frequency subbands and say, Alice take this subband, Bob take this subband, and so on. Now this is called orthogonal resource allocation, either time division multiple axis or frequency division multiple axis. There's actually another dimension of resource. It's called code. Now, we're not going to the details of signal processing or communication theory, but roughly speaking, it says that you're going to send the digital information in bits, right? 0, 1, 1, 0, 0, 1, 1, 1, like that. Okay. And what I'll be doing is to multiply your digital information on a much faster scale with a sequence of ones and minus ones. What's called a code. And these code will scramble your transmission almost into a noise-like, a random number-like sequence. And only the intended recipient will have the right code to decode that message. And the other receivers would not have the right code, and therefore they would not be able to decode your message. In a cocktail party analogy, this is like different languages. Okay. So if somebody is talking Spanish and another person is talking Korean, that will help to differentiate the conversation. Now, of course, it is only an orthogonal resource allocation if these codes are ideal, in the sense that they can perfectly differentiate the conversation. Just like in languages, sometimes the same pronunciation are valid in different languages. They just may have different meanings in different languages. In practical CDMA, it's actually non-orthogonal. There will be interference still. For example, in the uplink, different mobile stations have different clocks. In the downlink, there still might be channel distortion and shifts the signal. So in any case, a practical code division multiple access CDMA is non-orthogonal. Okay, you're effectively sharing a common resource in the air among interfering users. This doesn't sound like a very attractive idea at the beginning, but as history showed, it turned into an extremely successful technology. It started by a company called Qualcomm, which has since become one of the pioneers of many wireless technology innovation. And that was back in the late 80s. And then after quite a few years of debates in the 90s, it finally got standardized as so-called ICE95 as one of the 2G standards, and got very popular in US for certain operators and in certain parts of Asia. And then in third generation, both main tracks of 3G, one is called UMTS, the other is called CDMA 2000, actually use elements of CDMA technology. Okay. So if you're using a 3G phone, then you are using CDMA.